Chapter 21. Now we deal with unsaturated and aromatic hydrocarbons. In Chapter 19 we dealt with saturated hydrocarbons, which had no double bonds. But here we will have double bonds. So unsaturated hydrocarbons, they enhance our standard of living. They're used to make polyethylene plastic bags and bottles, polystyrene styrofoam cups, plastic wraps. All three of those are from polymerization and will be covered in next chapter in the polymer chapter. Unsaturated hydrocarbons are necessary in cosmetics, medicines, flavorings, perfumes, detergents, insecticides, and dyes. And so they're found across in many areas of our lives. There are many types of unsaturated hydrocarbons. Alkenes have double bonds. And if you have two double bonds, it's an allene. And so this does exist. You can have two double bonds on each side of the carbon. That's now an sp hybridized carbon, but you can have two double bonds on each side. You've already seen carbon dioxide. We put an oxygen there and an oxygen there, and that was in Chem 1. But in organic chemistry, we'll see that you can also have carbons there too. And so those molecules show that one carbon can have two double bonds. Alkynes, those are triple bonds. When you have a triple bond, the other bond is a single bond. In aromatic compounds, aromaticity is a special case. It looks like it's alternating between single, double, single, double, single, double. But actually, if it's an aromatic compound, it's not. The electrons delocalize in that circle, and it becomes its own unique entity. So all aromatic compounds will have this benzene ring. And that is benzene. That is a benzene ring. And anything that has that benzene ring will become an aromatic compound. And they got named that way because a lot of molecules that are in perfumes or smell really good have these aromatic signatures, and so that's why it got named aromatic compounds. But really, technically, aromatic compound just means it has at least one benzene ring somewhere in the molecule. All right, carbon atoms connected to double bonds contain 3 sp2 orbitals and 1 p orbital. The sp2 orbitals, these correspond to the sigma bonds. So in this case, we're taking 2 p orbitals and an s, and we're throwing them into a blender to make our 3 sigma bonds. And then 1 p orbital is left alone to make the pi bond, the double bond. So the double bond is made with the p orbital. The double bond is just p orbitals. The 3 single bonds, for example, we've seen this before. Carbon has a double bond coming off of it and 2 single bonds. Each of the single bonds is a sigma bond. That's the Greek letter sigma. And in the double bond, one of them is a sigma bond and one's a pi bond. And they're very different chemical bonds. The electron density in a sigma bond is between the two nuclei. So if I have a carbon here, the electron density is in between the two carbons. Whereas in a pi bond, it's above and below, actually. And so here we have, when we had unsaturated molecules, you just had 4 single bonds. So we had 4 sp3 bonds. Now we have 3 single bonds and a double bond. So we have 3 bonds that are sp2 hybridized, and then a double bond that just has p orbitals. And so here we see that hybridization. Note the sigma bonds, the 3 single bonds, are sp2 hybridized. Now the double bond, the pi bond, just uses these p electrons, which are above and below the plane of the atoms, whereas the sigma bonds are in the plane of the atoms. And so when we see these bonds, the sigma bond is in between the two atoms. The pi electron density is above and below. And again, the pi bond is a lot weaker than the sigma bond. If we have a triple bond, now we have just 2 single bonds. Let's look at my carbon. Let's say I have a triple bond to another carbon. We have a single bond there, one in the middle, and one at the end. So we see here that is where the sigma bond densities in between. We have two double bonds. And so again, one of the double bonds is left and right. That's one bond. And one of the double bonds, the electron density is up and down from the plane of the atoms. And it kind of forms a barrel of electron density around the atoms. But notice, the sigma bonds are in the same plane as the atoms. The pi bonds are above and below and to the left and to the right, and they form kind of like a barrel around the atoms themselves. So identify the hybrid orbitals around each carbon. This carbon, from the line drawing, we can see we just have 3 bonds to hydrogen. It's an sp3 hybridized carbon. It just has 4 single bonds. So if we actually draw out the understood hydrogens, you see that. 4 single bonds, sp3 hybridized carbon. This one is sp2. And this carbon is sp2. And again, there's an understood bond to hydrogen there. They each have 3 single bonds and then a double bond. And then these carbons again are sp3. They have 1 carbon-carbon bond and 3 carbon-hydrogen bonds. IUPAC rules for naming alkenes. You end with ene. So the ane of an alkane becomes ene. So propane becomes propene. Ethane becomes ethene. Butane becomes butene. Alkenes get ene endings. And then later we'll see alkynes get YNE endings. When we have to number, because now we have a double bond, there's 2 ways we could number this. 1, 2, 3, and it could be 3 butene, or we could number from this side and get 1 butene. And that's more correct. Lower numbers are always more correct. And so that's why you have to number from that side, because it puts the double bond on carbon 1, which is a lower number than 3. And we have an isomer, 2-butene. It's still butene, but the double bond is in between carbons 2 and 3. So we have 2 possible ways to have butene. Here we have 3-methyl 1-butene. Again, in this case, the double bond takes precedence over the branched methyl group, and so you want the lowest number on the double bond. We'll see a priority list later of which functional groups get priority when you number, but so far, alkenes get priority over alkyl branch groups. And so again here, you put the double bond on the lowest number of carbon, and that's why that's carbon 1. What is the structural formula of 4-methyl-2-pentene? Well, we first draw pentene, and it's 2-pentene, so the double bond's coming off of carbon number 2. So it's between 2 and 3. And again, it gets named for the lower one that it's touching. And then at carbon 4, there's a methyl group. And so here we have our answer. What is the name of this compound? Well, we need to find the longest chain that has our functional group. That is a 1-pentene. Then on carbon 2 there's an ethyl group. So we needed the longest chain that had the functional group. It would be longer if we went this way, but it didn't have the major functional group. And so it's 2-ethyl, 1-pentene. Geometric isomers. There is no rotation around a single bond. Around a double bond. There is definitely rotation around a single bond. Because in a single bond, the electron density was in between the atoms themselves. And so they're free to rotate around that bond. With a double bond, now we have electron density above and below, and those lock them in place. Because if they tried to rotate, it would twist. They can't spin like the middle ones can. And so once you have a double or triple bond, there is no rotation, which gives us geometrical isomers, because now these two are not the same. This is a cis compound because both of the major substituents are on the same side of the double bond. They're both on this side of the double bond. And here we have a trans because the two major substituents are on opposite sides of the double bond. They are trans of the double bond. And again, this is important now because there is no rotation around a double bond, so it's locked in place. This didn't matter with a single bond because they were free to spin as much as they wanted to, but now there's no spinning whatsoever. And so we get geometrical isomers. And again, with A's, the A's are cis to each other right here, and the A's are trans to each other here. Cis and trans occurs across double bonds. If one of the carbons has two of the identical elements, then there is no cis or trans, because you can just rotate the molecule and get the exact same thing. So this is neither cis nor trans. Because this molecule is no different than this one. All you do is take this molecule and flip it. But they're the exact same molecule, so they're not isomers of each other. So whenever one of the carbons has two of the exact same things at both spots, there is no cis-trans isomerization, because you can just flip the molecule and you get the same thing. Draw the chemical structure of cis-5-chloro-2-hexene. Well, we first draw 2-hexene. 1, 2, 3, 4, 5, 6. And the double bond is in between 2 and 3. And now it's 5-chloro. So at position number 5, we have to have our chlorine. 5-chloro-2-hexene. And this molecule is cis, because of the two atoms bonded to carbon 2, this is the bigger one. And of the two groups on carbon 3, this is the bigger one. It's way bigger than hydrogen. And so since the two groups, the two big groups, are on the same side of the double bond, we have a cis isomer. So is this cis or trans? Well, here on this carbon, this is the bigger atom. Methyl is bigger than hydrogen. And here, ethyl is the bigger group. So let's look at carbon 3. We have an ethyl group attached to it, and that's bigger than methyl. So this is trans. So that is trans 2-methyl-1-pentene, because the two big groups attached to the carbons with double bonds are on opposite side of the double bond. Many compounds have more than one carbon-carbon double bond. So if you have two carbon-carbon double bonds, you have a diene. And we'll see in next chapter, butadiene is used in polymerizations. 3 carbon-carbon double bonds are trienes. Cycloalkenes are like cycloalkanes, but have a double bond in the cyclo structure. And you start the name with cyclo, but you end in ene. So cyclopentene, cyclohexene. In here again, if we're going to put substituents off of it, they get the lowest number possible. And in general, carbon 1 always has the double bond, because you want the double bond on the lowest numbered carbon possible. So here we have 1-methyl-cyclopentene. Here we have 1,3-dimethyl, because there's a methyl group there, and there's a methyl group there, and that guy's carbon 1. It's kind of hidden by the text. 1,3-dimethyl-cyclohexene. We have two double bonds, 1,3-cyclohexadiene, because you want the double bonds in the lowest number possible. And here we see 4-ethyl, 1-methyl, 1,3-cyclohexadiene. That's a lot, so let's look at it. First, the 1,3-cyclohexadiene is right there. We have a cyclohexene group with 2 double bonds, so it's a cyclohexadiene. And then off of carbon 1, we have a methyl group. And off of carbon 4, we have an ethyl group. And in the end, most chemists will use the program ChemDraw to verify a name, because even for chemists, this can get confusing, because you could put the ethyl group on carbon 1 and the methyl group on carbon 4, and that's, I mean, it's just slightly less correct. Everyone knows what you mean, and as chemicals get bigger and bigger and more complicated, the naming becomes more and more nuanced. So don't worry too much about the finer nuances of naming organic chemicals at this stage of chemistry. Name the following compound. Well, here we have a cyclohexene, and off carbon 1 is the bromine. So we have 1-bromo, 4-methyl cyclohexene. Here we have 2-methyl, 1,3-cyclohexadiene. And we named it this way because you want the lowest numbers in the double bonds. Making this carbon 1 would have made this guy 2, 3, 4. It would have been 1,4-cyclohexadiene, which is not as low as 1,3-cyclohexadiene. So in this case, the numbering system for the substituents is always based on the double bonds inside the ring. And that's why this is carbon 2. 2-methyl, 1,3-cyclohexadiene. 2 examples of alkene preparation are cracking and dehydrating alcohols. When you crack alkanes, you just put under a huge amount of heat with pressure and a catalyst, and a gigantic alkane will split into a littler alkane and an alkene. Dehydrating alcohols will eliminate water and form a double bond. So here's cracking. We crack our molecules and we get alkenes coming out, or alkenes and smaller alkanes and hydrogen coming out. And here we're using a silica alumina catalyst. And this is done in the petroleum industry all the time, because you can take heavy, less useful fractions of petroleum and crack them down into much smaller, much more useful fractions, which can be sold off for many more purposes. Dehydration of alcohol. We see we eliminate water and form a double bond. And this requires acid as a catalyst. Why? Well, because we need an atom of H plus here to start the whole reaction. Here's our H plus. And now this oxygen has free electrons. A pair of electrons will come and bind it, forming this molecule. And now the positive is on the oxygen. Now this is H2O if it leaves, so water is a good leaving group. These 2 electrons go to the water, and water leaves the molecule, leaving a positive charge in this carbon. We have a carbocation. And now these 2 electrons come here, and an H plus floats away. And we form our alkene. And this H plus will then catalyze the next reaction. And so again, this reaction is acid catalyzed because the hydroxyl group needs to gain that 1 H plus to form the leaving group of water, which then keeps pushing the reaction forward. And so it's a catalyst because I started with 1 ion of H plus, and then at the end I get my H plus back, so I can start the next reaction, and then I'll get it back and I can start the next reaction. And so in theory, just 1 H plus could catalyze my entire reaction. Draw the cis and trans structures for the dehydration product of citric acid. And here is my molecule. So there's only 1 alcohol here. You see a lot of OH groups, but this is a tricarboxylic acid. That's a carboxylic acid. That's a carboxylic acid. That is a carboxylic acid. This is my only OH. And so I'm going to dehydrate here. And it doesn't really matter what side you choose because they're both identical. In reality, you would choose both. Just randomly. Sometimes it would be this hydrogen. Sometimes it would be this hydrogen. And when we get cis products, both of the big groups are on the same side of the double bond. And when we get trans products, we get the bigger group here and the bigger group here. Notice these aren't actually identical. They look really similar, but we have that carbon here in between the carbonyl and the double bond carbon, and that's not here. If they were exactly identical, then there would be no cis or trans, but they're not exactly identical, so we have the trans product. Physical properties of alkenes. They're very similar to alkanes. They're nonpolar, they're insoluble in water, and they're very soluble in organic solvents. And here we see ethene, propene, butene, 2-methylpropene, and 1-pentene. And we notice ethene, propene, 1-butene, and 2-methylpropene, which again is an isomer of butene, are all gases at room temperature as we'd expect.